Hello everyone, I hope you're doing well. So in this video, we're going to discuss Geeks for Geeks problem of the day, and today's problem is minimum BST sum subtree. So I believe that today's problem was very interesting as it is a hard level problem, but the problem statement was very poorly written, and there are certain things that you won't understand by just reading the problem statement. So the problem statement is very small, but there are a lot of missing details. So we see that the problem statement says that we have been given a binary tree. So remember, it's just a binary tree and a target sum, right? We need to find the length of the minimum subtree with a given sum equal to the target, which is also a binary search tree. So there are two conditions here. We need to find some subtree in this particular tree such that the sum of all the nodes is equal to the given target, as well as the subtree satisfies all the conditions of a binary search tree, and we have to return the length of the minimum such subtree. So the confusion that I had was, what do they exactly mean by the length? So after submitting one or two wrong submissions, I realized that by length they mean the number of nodes in the subtree, right? You need to remember this. By length they mean to say that they want the minimum number of nodes required in the subtree, right? So if there are possible subtrees which have the same sum, we need to return the one with the minimum number of nodes, right? So we don't even have to return the subtree, we just have to return the minimum number of nodes in which it is possible, right? So let us see how this problem can be done, but let us first discuss a sample test case. So this is the sample test case that has been given to us. So if you carefully see, then the subtree 5, 7, 17 and 16, if you add all of these three values, 5, 17 plus 16, it will give me the answer 38, right? So we require 3 nodes minimum to make the sum equals to 38. So the answer will be 3, and you can check that this satisfies the condition of a binary search tree, right? At 17 is greater than 5 and 16 is lesser than 17. So this this is the very general thing about this statement. The problem statement is itself not very difficult. If you know about binary tree or binary search tree, then you won't have any difficulty in understanding the problem statement. So there's nothing much to explain in this particular test case, but let me just discuss a few other things. So while we are actually going to implement this particular problem, what we can do is we can break the problem into two parts. So the first part, let me just break the problem into two parts. So part one will consist of just finding the nodes, find subtrees, or let's say the root nodes for the subtree for which sum is equal to target, right? So in the first part, we just find, we don't care whether it is the minimum subtree, we don't care whether it is a binary search tree, we just need to find all the subtrees for which the sum is equal to target, right? So this is our first criteria. This is what we are going to solve in part 1. Now part 2 will consist of going through all the nodes or going through all the subtrees which we have just found and check whether they are BSTs or not. If there is BST, it is an actual BST, then we have found our answer. Otherwise, we just move on to the next subtree. So check for all subtrees whether it is a BST. It is a BST, right? So this is what we are going to do. We have divided the problem into two parts. In the first part, we're just going to check all the subtrees for which the sum is equal to target, and this is actually the easy part that we can do. And the second part is not very difficult, but it's a bit tricky because you will have to take care of certain things, right? So in the part 2, what we have to do is we have to check whether the given subtree is a valid binary search tree or not, right? So let me just discuss the first part first. So the first part is not very difficult to implement. It's very simple. So if the value x is here, the value y is here, and let's say a and b. So you just try to go to the child, right? Whenever you reach a null pointer, whenever you go to the child of x, it is a null pointer. We just return 0 from here. When we come back to here, we return the sum of left subtree. For x, the total answer will be sum of left subtree, sum of right subtree, plus value of x, let's say, right? So for this particular node, the total sum would be this. So since left subtree and its right subtree are 0, because it is null pointer, it will return 0. Total sum for this particular node will be x. Now similarly for y, the total sum will be y, and same for a and b. Now when we go to the to its parent, to the parent of x, then for this particular node, the sum of left subtree would be x, the sum of right subtree would be y, and let's say it had as initial value p. So total sum will be x plus y plus p for this particular node. Now when we return from this particular node a and b, for their parent, the sum of left subtree is a, the sum of right subtree is b, and let's say it had an initial value q, right? Similarly for the root node, the sum of left subtree is x plus y plus p, the sum of right subtree is a plus b plus q, and let's say its initial value was z. This is the total sum for the root node. So this is how we are going to calculate the total sum for any of the nodes, right? Now what happens when we find that the current node has the sum equals to the target sum? So if let's say this particular node has the total sum equals to the target sum, let's say x plus y plus p is equals to the target. That means that for a subtree for which this particular node is the root node has the total sum equals to the target. So this is the subtree that we are talking about. This is the total subtree. Right, this is my subtree for which the total sum is equals to the target. So once I know the total sum for this particular subtree is equals to my target, I can store this particular root node for this subtree somewhere in any data structure. So I can store it in a vector, I can store it in a queue, anywhere I want. So let's say I have a collection of nodes. So I'll have node 1, node 2, node 3, node 4, right? So let's say I have a collection of these nodes. Now I know already, as I've pre-computed, that the subtree starting from node 1, the subtree starting from node 2, node 3 and node 4 all have the total sum equals to the target value, right? Now I can just check them individually. I can just check all the nodes one by one and tell whether the particular node is a BST or not. If the current node is a BST, I can say my answer as answer is equals to minimum of answer comma size. So size here would be the number of nodes present in the subtree of node 1 and node 2, node 3, node 4 respectively, right? So this will be calculated for all the nodes, and at the end I can just return my answer. So the next problem is, so we have already discussed how we can just traverse through the tree and find what are all the nodes at which the target is equals to the sum of the subtree. Now the next task is to check the binary search tree, whether the current binary tree is a binary search tree or not, or the subtree starting from the current node is a binary search tree or not. So binary search tree checking is not that straightforward. Like you might believe that we just need to check the current node, the left node and the right node, right? So if this is x, this should be some value y less than x, and it can be some value z greater than x, right? So there are also cases where this condition is satisfied, but if we go further down in the tree, then that would be wrong. For example, if 10 was here, now if this is 17 and this is 8, right? So you see that the value 10 is here and this value is greater than 17 is greater than 10. That is correct. It is present to the right of 10, and 8 is present to the left of 17 and it is lesser than 17. So this might also seem correct, but this is not how it should work. We need to check all the minimum node that is present in the right subtree of 10, right? We need to check the minimum node in the right subtree of 10 and make sure that it should be greater than 10. Similarly, if we have a left subtree of 10, we need to check in the left subtree of 10 the maximum value that we have, and we need to make sure that it is less than 10. So let me just write it for you. So the first condition for any node that we have to check is max element in left subtree should be less than current element, right? So this is my condition. Similarly, minimum element in right subtree should be greater than current element. This is our condition, right? So for example, if I have a subtree right here and it has some nodes like these, so for every node in this particular subtree, these two conditions must satisfy. If one of the nodes does not satisfy either one of those conditions or both of those conditions, then the given subtree would not be a valid binary search tree, right? And talking about the size or the number of nodes in the binary search tree, whenever you visit a node, you can increment your size counter or any variable you want. So this data part is not very difficult. Whenever you visit a new node like this and then this node, you can just increment a counter variable, right? But checking a binary search tree is a bit tricky because you need to make sure that these two conditions are satisfied. Now the next task is, how do we find the maximum element in the left subtree and the minimum element in the right subtree? This is also not very straightforward, but we can do it while we were calculating the total sum, right? So while we were calculating the total sum, we can calculate this information also, right? So that we don't need to traverse the whole tree again. So for this particular node, the maximum node in the left subtree should be minus infinity, right? So I'm talking about the case when the child is null pointer, right? So for the leaf node, the maximum element in the left subtree should be minus infinity and the minimum element in the right subtree should be infinity, right? So let's say now this value is x, so minus infinity would definitely be lesser than x and plus infinity would definitely be greater than x. So for this particular node, the condition is satisfied. Now for this particular node, when I go to its parent, I know what is the left child of the parent, right? So let us denote this as p. This is the parent of x and this is y, right? For my current node, I need to return some value or some information to the parent, and that particular information would be the max and the minimum value for this particular node, right? So the maximum value for this particular node is x and the minimum value for this particular node is x. How do we calculate the maximum and the minimum value? We calculate the maximum value as max of the value x and left dot max, that is the maximum value from the left subtree, and right dot max, that is the maximum value from the right subtree, right? Although like if we have checked for the current node, then definitely the value of right max would always be greater than left max, but this is what I just have written while I was implementing the code. Although I believe that this part would not be very important. If you're considering the max value, only the right max would be important. Similarly, the minimum value for the current element or the current node can be calculated as x comma left min comma right min, right? So again, right minimum is something that we don't actually require because the minimum value will always be contributed by the left subtree. But again, this is what I just wrote like while I was implementing the code, and that is why I've written it here, right? So p for the node p or for the parent p, it will get a minimum maximum value from the left subtree and the minimum maximum value from the right subtree. So for the left subtree, I need to care about the maximum value that it has returned, and for the right subtree, I need to care about the minimum value that it has returned. And again, I have to check these two conditions: what is the minimum value and what is the maximum value, right? So for every node, I am calculating two values: what is the minimum value for this particular node and what is the maximum value from this particular node. So when I'm saying the maximum and the minimum values for the current node, that means what is the maximum value present in the subtree of this node and what is the minimum value that is present in the subtree of this node, right? Now what I can do is, when I'm going for the parent, I can just check what is the maximum value that is present in the subtree of this particular node, right? Because I needed that particular information, that is why I have stored it earlier. And for this particular node, I need what is the minimum value for this particular node. I need what is the minimum value in the subtree of this particular node y. right? So when I've calculated these maximum and the minimum values, what I can just do is I can save this value somewhere. So for example, I've created a map. So let's say it's of type node, and it will store a pair. So what information will be present in the pair? So for any node, I will store only the useful information that I need. So the most useful information that I need is the maximum element present in the left subtree. So I need this information. So I'll store in the pair left.max. For every node I am doing this, and for the right subtree I am storing the minimum element. So I'll be storing right.minimum. And while I will be checking the BST, I can just check whether this value is true or not, right? So one thing more that I can do is, like, instead of saving this information, I already know what is the left max and what is the right min. I can check whether the current subtree is a valid subtree or not. And since there is a way to calculate the size of the subtree or the number of nodes in the subtree, then I can check all the conditions here only. I don't even need to implement the second part. I just explain it in this way, because this if you divide the problem into two parts, it is much easier to write, as well as it is much easier to understand. Otherwise, you can always do all the things in the same function, in the same initial function that we will be using to calculate the sum, the minimum and the maximum values, right? So this would be the whole solution of today's problem of the day. And I know, like, all the things, there's a lot of information to process, so I'll just quickly summarize through what I just said. So we have divided the problem into two parts, and we will be dealing with these two parts independently, right? We will be dealing part 1 first, and then we will be dealing part 2 second. Although it is not necessary to divide the problem into two parts, it is always possible that you can, like, do all of the things in a single function, and it is very well possible, and it will also give the correct answer. But I have divided into two parts just for the sake of simplicity of understanding, right? So in the first part, what we will be doing is, we will be finding all the subtrees for which the sum is equal to target, right? In the second part, what we will be doing is, since we already have the subtrees, we will check for all the subtrees whether it is a valid binary search tree or not, right? So this is what we are going to do. Now the first part is fairly simple. You must have studied, if you have done some traversals on trees, then you must have already done these kind of problems where we calculate the sum of the subtree for any given node, right? So talking about the next part, which is very important, how do we check whether the subtree is a valid binary search tree or not? So to check whether a subtree is a valid BST or not, we need to make sure for every node in the current binary search tree, the maximum element in the left subtree is less than the current element, and the minimum element in the right subtree is greater than the current element, right? So for every node, these two conditions must satisfy, otherwise our subtree will not be a valid binary search tree, right? So this is our main condition. Now how do we find the size of the binary search tree? So by size, they here mean the number of nodes in the binary search tree. So it can be easily calculated whenever you will be testing out this particular process, whenever you will be testing whether the current tree is a binary search tree or not, or whether the current subtree is a binary search tree or not. What you can do is, whenever you visit a new node, you can just increment some counter variable, and at the end, the value of this counter variable will be the number of nodes in the binary search tree, right? So this is how we are going to implement this particular problem. Now let me just show you the code of this particular problem and how I have implemented it. So there is a lot of code here. So initially what I have done is, I have created a struct called imp data. So by this I meant important data, and it will be storing three values for every node: the minimum value, the maximum value, and the sum, right? Now in the main function, what I've done is, I've created an infinity value that is equal to 10 to the power 9. I've created a cube. So this is for storing all the nodes for which the subtree sum is equal to the target value. And I've calculated a map called min max. So this will be storing this information. What is the maximum element in the left subtree and what is the minimum element in the right subtree, right? So this map is used to store that information. Now this is my traverse function. So we'll talk about the traverse function later on. So I'm calling this traverse function here, and I've initialized my size with 0. And here's my check BST function. So again, we'll be talking about these two functions later on, but let us discuss the main logic first. So I'm calling the traverse here, and I'm initializing my size with 0. So this will be the size of the current binary search tree. right? And at the end, I am initializing my answer with infinity. And since my queue has all the elements for which, or all the nodes for which the subtree value is equal to the target value, I can just check whether this particular subtree is a valid binary search tree or not. If the particular subtree is a valid binary search tree, I can set my answer as minimum of answer comma size, and I'll reset my size to 0. So size is a global variable that I'll be using, and I can just pop the current element from queue. So for all the elements in the queue, I'll be doing the same thing. I'll be checking whether the current subtree is a valid binary search tree or not. If it is a valid binary search tree, I'll update my answer as minimum of answer comma size, and I'll just pop the current element from queue while resetting the size, while resetting the value of the size. At the end, if the answer is equal to infinity, I return -1, because that means I have found no valid binary search tree, and otherwise I return my answer value. So now let us discuss what is inside these traverse and the check BST function. So if I talk about the traverse function, whenever I reach a null pointer, what I do is I create a new data. So this particular data will store the minimum, maximum and the sum value. So the minimum value would be infinity, the maximum value would be minus infinity, and the sum value would be 0. Right. So I just return this new data. Now I get some data while traversing from the left, I get some data while traversing to the right. So I used this depth thing earlier, but this is not required, so you can also remove it. I was using it for something else, but at the end how I implemented it did not require the depth value, right? So I just get some data from the left, I get some data from the right. So the current sum will be equal to left sum plus right sum plus current data, right? So I have tried my best to write a very clean code and write useful variable names so that it is easier for you to understand, right? Now I check whether the current sum is equal to target, then I push it into the queue, right? What do I push into queue? This is the current node. So if you see that this is the node that I am getting, and I've pushed it into the queue. Now for the current node, I am initializing the data. The sum would be the current sum, the minimum would be minimum of current data, left min and right min, the maximum would be current data, left max and right max, right? So this is the maximum of all these three values, this is the minimum of these three values. Now for the min max of current, this is the current node, I am just storing the useful information, that is the maximum element in the left subtree and the minimum element in the right subtree, and I just return new data. So this was this was all about the traverse function, and let us just talk about the check BST function. So what I do is whenever I reach the null pointer, I just return true, and whenever I reach a new, that means I have to increment my size, so I increment my size. Now I check whether the maximum element in the left subtree, which will be stored in the first value of this pair, like you can see it here, the maximum value of the left subtree is greater than or equals to current data. That means that it is not a valid BST. It is it is not satisfying this particular the first condition, so I return 0, and I check whether the second element, that is the minimum element in the right subtree, is less than or equals to current data. Again it is not satisfying the second condition, so I just return 0 from here. So if both of the conditions are satisfying for the current node, I return check BST of left node and check BST of right node. So they will return some boolean value, so I just take the AND of both of them, right? So if you want to merge these two functions, I'll be just giving you an overview of how you can do it. Since you already know what is the maximum value in the left subtree, what is the minimum value in the right subtree, you can just check it here whether the current node will be a part of a valid binary search tree or not, right? Now the other thing that you can do is, while you were returning from the child nodes, you can for every subtree you can calculate the number of nodes in that particular subtree, right? So you will have to maintain some extra variables, and here I was returning minimum, max and sum. Here you can just store one more value, what is the number of children in the current subtree. Now whenever this particular thing is true, whenever current sum is equal to target, then you can check for all the conditions whether the current subtree is a valid binary search tree or not, and also whether what is the number of children in the current subtree. So I did not do it here because it will be quite too much data in a single function, and also it will be difficult to explain as well as difficult to write. So that is why I have divided the problem into two different parts, and I hope that you guys were able to understand the solution this way. So this was all about today's problem, that is minimum BST sum subtree. So it is labeled hard, and I believe that today's problem was quite interesting. I hope that you guys were able to understand the solution and you guys enjoyed solving this problem. So if you did, then consider dropping a like on this video. Don't forget to subscribe to this channel. It's always free of cost, and if you don't find the videos interesting later, you can always unsubscribe. So till the next video drops, keep coding, stay safe, bye bye.